Hi. Estimation is valuable, but I'd like to show you that it could also be like a work of art. Before that, though, I want to indicate that estimation is also developed in the canine world. I'll first show you that. Here's Fluffy, our Labradoodle, and he's got a scent. He's excited. Okay, I first want to go out here and show you what I mean about Fluffy having a sense of estimation. A few weeks ago I was out here, and Fluffy happened to be beside me, and we came over here. There he is, there he goes, sniffing around. And we came over here, and out there, a bunny rabbit hopped up. And Fluffy took off after it, but only for a couple seconds. He took off after it, and then he stopped. And then he just sauntered out there slowly. And the point is that he had estimated that he couldn't catch the rabbit. And so he just took his time. Okay, for the human example, I want to go to the blackboard in the cabin. So I'll go into the cabin and I'll talk about that. Hey, Fluff. Good doggy. Now, that should do. I would like to mention Enrico Fermi, an Italian physicist who was a master of estimation. He picked up a Nobel Prize in physics in 1938, and he moved to the USA in 1944. Okay, I want to get a particular example of which Fermi would have been a complete master of, and that is a canine example again. If you're like me, you've probably marveled at how well a dog can trace a scent. You know, how does a dog do that? And so I want to raise one possibility, is that the dog just smells the soles of his shoes, or what's come off of the soles of his shoes, and he follows it that way. Maybe, maybe not. You could Google that and find out what other people think. Okay, so, but my Fermi question is the following. When I'm walking around in boots, say these rubber boots on the property, then per step, how many molecules are shed? Right, that's going to be our question here. And all right, is that? So the Fermi method is to quickly estimate, as accurately as you can, but quickly, an answer for almost any question. Okay, so our question is going to be, per step, how many molecules? Now the molecule is the smallest bit of matter that has this chemical property of the substance. So rubber molecule still smells like rubber. Okay, that's a question. And you might say, well, I don't know, or your first impulse is to say, I have no idea. But if you think about it, you can actually get a fairly robust answer. Okay, so how I'm going to do that is have a look at these boots. They're obviously worn out, but they're also worn off here at the heel. And so what we're going to do is estimate first the amount of rubber worn off. So it's a couple inches that way, an inch that way, and maybe an eighth of an inch thick what's worn off. So we're first going to estimate the rubber worn off, and we'll call that the volume of rubber. Well, it's something like, I'm just estimating here, 2 inches by 1 inch by maybe an eighth of an inch thick. But we're going to be dealing with molecules, and down at that level, almost everybody in the world uses the metric system. So I'm going to write that in terms of meters. And so instead of 2 inches and 1 inch, I'm going to say something like 5 centimeters times 2 centimeters, just roughly, times 2 millimeters. Well, how much is that? 20 times 10 to the 3, 4, 5, 10 to the minus 7 cubic meters. So, okay, 20. I should be not a dot, but a 0 there. 20. Okay, that's one number. That's the volume of rubber. Now, what is the volume of a molecule? Of a rubber molecule. Now, I had forgotten what rubber was made of, so I Googled it, and I find that rubber is C5H8. Okay, some carbon atoms there. And atoms, the hydrogen atom is about 1 angstrom in diameter. And an angstrom unit equals 10 to the minus 10 of a meter. Okay, so the smallest atom is about an angstrom across. Okay, so for the volume of the molecule, I'm going to take, okay, there's a few stuck together there. I'm going to take them to be 5 angstroms. It's a chain more, but I'm going to just take this to be 5 angstroms by 5 angstroms for the volume times 5 angstroms, right? Because it's not a single atom, it's several atoms put together. And what does that become? 125 times 10 to the 10, 20, 30, minus 30 cubic meters. Okay, so now it's already looking promising. We can get the number of molecules, just the total number of molecules in the taken off part of the boot, by just dividing those two out. And so the number of molecules equals this one divided by this one, which is 20 times 10 to the minus 7 over, we'll say 12.5 times 10 to the minus 29 equals how much? We're just talking rough here, about 2 times 10 to the 22nd. Okay, that's the total number of molecules in the rubber worn off the boot. Okay, per step, how much is that? That's a lot of molecules. Per step, I take. Well, I get a pair of boots like this about every 2 years, I figure. And I walk on the property maybe once every day or 2 or 3. And so I'm going to take 300 days. I walk in these boots, say, 300 days in a lifetime. And times how many steps per day? Maybe 1,000. Times 1,000 steps. 1 kilometer. 1,000 steps. Which is 300,000 steps I get out of that. That may be right. That may be probably pretty close to being right. And so what is the number of molecules per step? Just divide this number by that number. And so I have, whoops, Fluffy wants in. 2 times 10 to the 22nd over 0.3 times 10 to the 6 equals 3 goes into 2. About 6 times 10 to the 16. Oh, I see somebody wants in. So this is the number of molecules per step. I'll let Fluffy in. Come on in, Fluffy. Good doggy. Okay, you can be here. So how big is this number? Well, 16 is equal to 9 plus 6 plus 1, 16. And so this number is, the 6 is not important, but the 10 to the 16th is equal to 10 to the 9th times 10 to the 6 times 10. How many molecules per step? 10 million billion. Okay, so with all those molecules given off per step, is it a wonder that Fluffy can track me, or other dogs can track other people? Okay, it's just a thought. But my point is that this is an estimation I got an answer, and something like 10 to the 16th. Number. Now, how close is that? How close do I expect that to be to a reality? Well, I say it's something between 10 to the 15th and 10 to the 17th, somewhere in that range. See, so I don't care too much about accuracy, but you can see you can narrow it down quite well down there. What you got? Okay, that's my first Fermi example of a problem solved in the Fermi method. I want now, finally, to give you a question and to estimate. It's kind of fun doing it. It's fun making them up, and it's also fun getting answers. So here's one that I made up, and I did come up with an answer, but I will not tell you the answer today. I'll just give you the question today, and you can work on an answer if you want to. And if you get an answer that you're proud of or happy with or something, you could put it in the comments. Okay, here's my question. If you were to walk once around the Earth, you might take a year or two doing it, but walk once around Earth, on a circumference. What's the question? How many people would you meet? many people would you meet? And you're saying, I can hear it already. What do you mean? Maybe none, maybe some. My answer to that is on average. If there's any doubt about something, just average it out. So if you're wondering which circumference you're going to take, well, you want to say, this circumference I'm going to meet so many people, another circumference I may meet a different number of people. But on average, if I walked around, or you walked around the Earth one time, how many people would you meet? Okay, I'll leave you that. And maybe in a week or two I'll come back and I'll show you my answer for this. But in the meantime, have a good time trying. Okay, thank you.